so far, and extend a couple of things, make a few further comments. So in the first lecture, we had two definitions of the sphere, if you want, that are absolutely equivalent. Either I tell you in embedding coordinates what a sphere is by putting it in one more dimension, or I just tell you here is the metric, and that's it. I just have d-dimensional angles theta 1 up to theta d, and then from this metric you could go up there, and from up there you can go to this metric by picking a parameterization. Is it clear? You agree? You can go up and down. They are absolutely equivalent. ADS, it's similar. ADS, we defined it as an hyperboloid. And it would be nice, and we will do it today, not right away, but in a few minutes, to have another definition where we trivialize the ADS constraint. And then we would say ADS could be written by a metric where we don't need to think of it in terms of embedding it in anything. It just exists by itself directly in the dimensions. Okay, we are going to do that. This is even more useful than the sphere, because we would like to make sure that we have only one time and so on. As we understood last time, the hyperboloid is not really just the hyperboloid, it's the cover of the hyperboloid. That's what this tilde means. Namely, in this hyperbolic picture, time rotates these two times, x minus 1 and x 0. So at each point, one of the times only, or a combination of the two, is advancing. And to make sense of this picture, you don't want time to be periodic. You unwrap this, imagining you put many sheets here, right, like paper. And then when you go around, you don't come back to yourself. If you start on the first sheet, you go to the second sheet, third sheet, fourth sheet, and so on. Whereas the other directions, orthogonal to this circle, are space-like directions. Now, in the sphere, as you remember, is a very symmetric object. Geodesics on the sphere are just intersections of the sphere by planes. And this plane and this plane, they differ by a rotation. Whenever I have a plane, I can rotate it to another plane, and I rotate one geodesic to the other. More generically, or differently, points on the sphere, if I have 2 points, I can apply a rotation to always map one to the other. So all points are the same. There's no special point. Right? There's no, yeah. Everyone is the same. Now, the same is true in ADS. Right? In ADS, if I have a point, I can apply a rotation, for example, in this plane, x minus 1, x 0, to move it like this. And I could apply a boost that would change x minus 1 and x 2 to move it like this. So any 2 points, I can relate by a symmetry. Right? So any 2 points in this hyperboloid, I can map, I can find a point. If I have a vector x, I can find a vector x prime. And these transformations, what do they preserve? They preserve x squared. But that's exactly the definition of my space, right? So that's the definition of a boost. A Lorentz transformation is a transformation that preserves this. So I take a vector x and I rotate it to any vector x prime. So when I go from x to x prime, and then I ask what condition do x prime satisfy, it's the same condition. And so even though it looks like this point here is different from this point here, no, it's not. It's the same thing. This observer sees exactly the same hyperboloid as this one here. It's just exactly the same. Okay? In the same way that when we draw flat space and then we do a boost and the axis contracts, for another observer, that observer sees the same axis in the same way, and it's not any different. Now, what we will see now, that's the next thing we're going to see after the summary, is, so the analog of symmetries we have, 2 points are related by symmetry. So we learned that all points are equivalent. So it's what's called a maximally symmetric space. What we did not see here yet, but we will see in a few seconds, is the statement that geodesics can be described geometrically very nicely by just drawing planes that intersect, in this case, this hyperboloid. Now, this hyperboloid, you see that if you go in space very much to this direction, you would reach what you would call the boundary. So this would be what we call this the boundary of ADS. And the boundary of ADS is time. This time is R times a sphere of d minus 2 dimensions. So you see in ADS3, it's an S1, it's a circle. That was what we saw last time, that this is not disconnected from this. That's because we are only plotting 3 x's. If we were to plot x2 and x3, we would see that we could rotate from 2 to 3, right? So the boundary is a circle. And if there were more x's, it would not be a circle, it would be a sphere. Okay, so in ADS5, it would be a 2-sphere and so on, a 3-sphere and so on. Okay, so that's the topology. So this is really starts to look like a box. Like I said, it's like a cylinder. So like a filled cylinder, right? The boundary is the cylinder, so ADS looks very much like a cylinder, and we are going to make it explicit soon. The last thing we saw, or one more thing we saw, was this Polyakov Lagrangian that we write here, just a free particle. Now, if I gave you this Lagrangian, something that you saw in the notes, and that maybe I mentioned, maybe not, is that this condition, the velocity square, is constant. And it's constant because this Lagrangian doesn't depend explicitly on time, on this parameter time. So it's kind of a conservation of energy. I put energy in quotation marks because I want to reserve energy for a real energy that we are going to introduce soon. But it's the time independence of this Lagrangian with respect to this parameterization time. I don't want to call it energy because it's a parameterization time. It's something arbitrary that I could have chosen differently. But fine. Now this constant, we set it to +1. That nice choice means that this parameter t is the proper space along my geodesic. Now, if I were dealing with space-time, let me emphasize that in that case, I could set it to -1, and this would be what I would do if I had time-like geodesics and not space-like. And in that case, t would be not the proper length, but the proper time. And I would set it to 0 if I wanted to describe null geodesics. This is conserved, so once I impose it in the beginning of the geodesic, this is conserved along the geodesic, and this distinguishes the 3 types of the geodesics that you could have. Sounds good? Okay, so let's study then, let's start studying geodesics in ADS. And so let's do it. So we start with that Lagrangian. And the Lagrangian says that I should have 1/2 of the integral of x dot A, x dot B. And now I'm going to contract with this eta AB, this metric that I drew up there, this metric here. But then this would be flat space in d+1 dimensions. So what I should do is put a constraint that says I cannot move anywhere, I must be on the hyperboloid. So I add an extra field that's not dynamical, like this Ilbein or Heinbein, whatever it's called, that we introduced last time. Let's call it lambda. It's a new field. So that the equations of motion for lambda just set whatever I'm going to write here to 0. And what I want to set to 0 here is this x squared, so xc plus r squared. So that the equations of motion for this lambda set this to 0, but this puts me in ADS, right? Okay? The equations of motion for lambda, you see, they are just exactly this condition. That's it. So this Lagrangian, it's what's called the Lagrange multiplier, forces the point, this free particle, to be on the hyperboloid. Okay, good. So here it is. So now let's write so this is the equation of motion for lambda. So this is the lambda equation of motion. That just puts me on the hyperboloid. What about the x equation of motion? Well, the x equation of motion would be dd time, derivative with respect to time of the derivative with respect to x dot, of x dot, a, minus derivative with respect to x, that gives me lambda, times xa equal to 0. Right? So x double dot minus lambda xa equal to 0. All good? Now, we need to find lambda. Right? Otherwise, we cannot solve a differential equation if there is a field that depends on time here. So now that's easy, because we do the following. We take this equation, and this is a vector. We dot this equation with a vector x, and I get, let me use vector notation. Let me ignore the index. I get x dot product with double dot minus lambda times x squared equal to 0. Okay, this is all vectors. But x squared, by the lambda equations of motion, this x squared is nothing but minus r squared. And therefore, we learn what lambda is. Lambda is just x dot divided by r squared. And so the equation that we got right now is x double dot, let me put back the index a. Okay, I'll put a minus, but then we fix, maybe it's the wrong sign. The dot product x with x double dot divided by r squared times xa equal to 0. Is the sign correct or wrong? Let's see, there is a minus, there is another minus. I put it on the other side, so there is an overall minus. And here there was a minus, so it's plus. Okay. Good? Okay, let's hope the number. It doesn't matter. It does not matter, because I could define it here with a plus or with a minus. If I put a plus here, then this equation would fix it. That will, the sign I put here doesn't matter, because it will just redefine lambda. So that's irrelevant. That's irrelevant. Okay, good. So now we get this equation, and that equation is good, but it's not perfect, because you have two derivatives here and two derivatives here. And normally you don't like this type of differential equations. You like to have the term with two derivatives isolated so that you can evolve it nicely. If you have lots of derivatives everywhere, it's a nightmare to evolve. But that's very easy to fix, because you see that x squared is a constant, and that means that when I take derivative of this condition, I get that x dotted with x dot equal to 0. That just comes from taking derivative of the condition that x squared is a constant. But then if I take one more derivative of this equation, so this follows from x squared equal minus r squared. If I take one more derivative, I get that x dot double dot plus x dot square equal to 0. And so x dot double dot is just minus x dot square. And so the final equation we get is x dot dot minus x dot square over r square times x equal to 0. Or if I put the index a. So this is the geodesic equation, the equation that describes the geodesics in ADS. But we can do even more, because we know that this is constant. And therefore, this becomes x double dot a, and then x dot square over r square. This is nothing. X dot square is nothing but the velocity square. So minus 1 over r square times XA. Okay, let me put here hashtag, where this hashtag now I need to be careful, right? Because now I need to say that this hashtag could be -1, 0, or 1. Because I'm using now the condition for the velocity. And here we saw that the velocity square is equal to +1 for space-like, -1 for time-like, and 0 for null. So that's what we should put here. This -1 would be for time-like geodesics, 0 for null, and +1 for space-like geodesics. Okay? So this would be the final equation we get, which is a trivial equation. It's just harmonic oscillator-like equation. X double dot is equal to X times a constant. So it just says that X oscillates, right? Well, depends if this is positive or negative, actually. Let's be careful. Okay? Good. Okay. So let's continue studying these geodesics. So let's solve this equation. So let's think of a person in ADS. In other words, we want time-like geodesics. Right? I want an observer in ADS, or a rock that I throw. So it's some time-like geodesic. Right? So something time-like, we would get the following equation: X double dot plus 1 over R square X equal to 0. But then this equation is trivial. We know that X is just equal to a constant vector A times cosine of T over R plus another vector B times sine of T over R. That's the general solution, just an oscillator that oscillates like this. Do you agree? So that's it. So that's the general solution. Am I done? Not really. Let's set T to 0. When T to 0, what do I get? X equal A. Is X equal a point on the hyperboloid? For any A? No. So of course we need more conditions. So we need this, but we need the condition that A squared needs to be minus R squared, because I need to be on the hyperboloid. B also needs to be squared to be minus R squared, because when T is equal to pi over 2 times R, B must be on the hyperboloid. And now, if you want actually all points to be on the hyperboloid, you can easily check that A needs to be orthogonal to B. In other words, we have two vectors that are on the hyperboloid that are orthogonal to each other that define a plane. And then it's whatever that plane is, how it intersects the hyperboloid. Right? And so what we get is that the geodesic is, for example, this plane here. That's definitely a possibility. I just take A to be this vector. I take B to be this vector, right? A points in the direction -1, B points in the direction 0, and then the geodesic would be just the circle that goes around forever and ever and ever. But you see that you could do a boost and rotate this plane and find another plane. Oops. And this other plane would intersect the hyperboloid along some curve like this. And these two would be related by a boost. So this observer that goes around like this is another geodesic. And the two would be related by an analog of a rotation that in this case mixes time and space. It's what we call a boost. But you see in this yellow line, what is happening in this yellow line from the point of view of the red line? Imagine you are the red observer and you are just here moving in time. What do you see for the yellow line? You just see a particle, so here is you. You are just moving in time quietly. And then what do you see about the yellow? You see from time to time, there is the yellow guy that passes by you. Right? So you have something that's like a particle that's oscillating. So you are here, and you just see this yellow chalk passing by you, then coming back, then coming back. So you see a box. You see exactly a box. You see that if there is a particle that you throw away, the particle goes and comes back and comes back and comes back. What's the period? It's always the same. It's always 1 over r. You see, the period doesn't matter. All geodesics have the same period. So all of them, the period of rotation is just, all of them have the same period. 2 pi times r. Sorry, 2 pi times r. After 2 pi times r, this time comes back to itself. This time t. Okay? So that's the period. That is geodesics F. So let's see, what else do I want to say? No. I want to correct. Let me think 1 second. This is okay. Yeah, that's fine. Okay. Yeah, that's fine. Okay. Is there something more I want to say? So all these geodesics are equivalent. They take always the same period, 2 pi r, to go around. And yeah, that's good. Okay. Let me maybe make one more comment. That you could also consider these planes that you boost more and more and more and more. But all these planes are time-like, right? And you could boost, but at most you get to 45 degrees. In the extremum case, when you boost maximally, you see these yellow lines become more and more and more, this becomes longer and longer, this ellipse, right? And eventually, in the limit, they would become 2 parallel lines, one going like this in the back, and one coming like this in the front. So this would be the limit of boosting this infinitely, right? You boost more and more and more. You see, eventually, they don't meet, and they just go all the way to infinity. And you see that in that limit, where it becomes longer and longer and longer, you get a straight line, a null line, that is null. And the null line is a geodesic both in ADS and also in the embedding, because it's a straight line. So this straight line, the other ones know. This circle is not a geodesic in the embedding. In the embedding, geodesics are straight lines. But the limit, the null ones are. And that's a general thing, that if you have spacetimes that are conformally related to each other, geodesics are not trivially related except null geodesics. Null geodesics are. And that's why these planes that are here, eventually the null geodesics do become the same as the geodesics that would be if you lived on the plane. Okay? So if you are a being on this plane, this is not a geodesic, but because the plane is null, this plane, you do get geodesics. If the plane is something like this, then your geodesic would be this. This would be a space-like geodesic, for example, one that would go from here. I'm not going to draw it in the middle, not to screw up the figure, but this would be a space-like geodesic. And to study it, you would redo a little bit the computations, but making sure that you use the space-like sign, so you use 1, and therefore this sign is 1, not +1, but -1. And therefore, you would have to change these cosines and sines into hyperbolic coshs and sinches, and change a little bit, and now things would grow forever instead of rotating. Okay, so now let's go to this side. So we understood that ADS is a box, and now we really want to see this box. And that's easy to do. We just want to find the parameterization, a nice analog of these angles. So the first thing we see is that we had this condition here that I'm going to write down here in the corner, which was that x minus 1 square plus x0 square. I'm actually rewriting it, multiplying the full equation by -1, minus x1 square minus ... minus xd square equal to plus r square. So you see I multiplied everyone by -1. Was this d or d? It was d, it's good. And so you see that what equation satisfies x squared plus x squared equal to 1 is when one is a cosine, one is a sine. Right? Now we want something square minus something square. So what function does that? That something square minus something square equal to 1 instead of plus. Hyperbolic cosh and hyperbolic sinh. So let's try that. Let's say x1, x minus 1 will have some hyperbolic cosh of some variable. Let's call it rho. x0 will have some hyperbolic cosh also of rho. And then the other xi will have hyperbolic sinh of rho. And then let's try the following. Let me just say that xi is hyperbolic sinh times a unit vector in the sphere. So this is a unit vector. So basically it describes a sphere with d minus 2 dimensions. So this vector satisfies n squared equal to +1. And therefore the square of this part of the metric just gives sinh square. The square of this part of the metric I want to give cosh square, but that's trivial. And we know what we want to do. We want to put cosine of t, sine of t, because after all, that's what we said t was. It was the rotation between this 1 and -1. So this does the job. You see, the square of this plus the square of this is cosh square. The square of this is sinh square. So when I do this minus this, I get 1. And so it doesn't work because it should not be 1. It should be r square. So I'm just forgetting an r here, right? Just so when I square this minus square of this, it gives r squared. Okay? All good? Do you agree that this does the job very nicely? So now I just plug this metric into the flat metric, and I see what metric I get, and I get the following metric. First there is minus cosine hyperbolic square of rho times dt square. Actually, there's an overall r square, but I'll put it on the left-hand side so that I don't need to put a big parenthesis. So the metric is r squared times what I'm writing. The first term is minus a times square times a prefactor plus d rho square plus sinh square of rho times the metric of a unit d minus 2 sphere. And so this is an equally good definition of ADS. And it has the big advantage that I don't need this tilde or anything. Here, when I see this metric, I would never cross my mind to say that this t is periodic. I would just say t is something that goes on forever. I would immediately unwrap it. So here, it's done. I just have time, a radius, and a sphere. So this is ADS. Okay, so let's try to think a little bit and to digest a little bit this metric and see how it does make sense with respect to what we have been saying. Okay. So let me, before, just draw this picture, just draw how I would think of ADS in these coordinates. I would say time goes up. Then I would say there is a sphere, SD minus 2. And here I'm drawing the case of S1, otherwise I cannot draw. That sphere is there. And then there is a radial direction, that's rho. Okay? So this variable is time, this radial variable is omega, and this variable would be the angles of the sphere theta. And so ADS is this inside of this cylinder. So it's this box. Now it's not a finite box because rho goes from 0 all the way to infinity. Rho here goes from 0 to infinity. And when rho is very big, here, when rho is very big, the metric becomes approximately equal to e to the minus. So if I set rho equal to some big constant value, so if it's constant, I ignore this d rho because it's constant, and then it's big, so it becomes equal to some factor. That factor blows up, it's exponential of 2 rho, times minus dt squared plus the metric of a d minus 2 sphere. Do you agree? And this is nothing but a cylinder. Cylinder is a circle times time. So that's the boundary. But of course, it's asymptotically. It's times some huge factor. So as I go, it's bigger and bigger and bigger and bigger. And strictly speaking, it's infinite ADS. Okay? So it's an infinite box in the sense that if you ask, what is the proper length of this line? This length is equal to infinity. But if you ask, how long does it take when I throw a particle very, very strongly so that it goes very far away and then it comes back? And I ask, how much time does it take? The answer is finite, no matter how far it goes. For me, and who am I? I am this red observer. For me, this is always the same 2 pi r. Even though this length is infinite. And that's because space and time is getting deformed as I go there. So even though I go very, very, very far away, it's like in the twin paradox. For me that I'm here, it's always 2 pi r, no matter how far this guy traveled. And for the yellow guy is stopped, and it's the pink one that's traveling. And the yellow guy would say the pink one took 2 pi r to come back. So it's an example where it's really symmetric between the two. There's no asymmetry in that case. So let's just be careful with this 2 pi r. Let's just see how do we see this 2 pi r in these trivial coordinates. You see that the yellow line for the red guy, the yellow one came back after 2 pi, right? So t evolved by 2 pi, not 2 pi r, 2 pi. Do you agree? But that's not a distance, that's just a coordinate. So let's be careful. The yellow one evolved 2 pi. That means that this time here evolved delta t equal to 2 pi. But that's not the proper time for me. The proper time for me, there is this r squared here. If I am in the center of ADS, when rho is equal to 0, this factor is 1. If I'm in the center of ADS, this is 1, this is 2 pi, this is the interval of time, but I multiply by r. So the time that passes for me, that I'm in the middle of ADS, is 2 pi times r. So that's the time in my clock. yeah, but here is also 2 pi square, and I take the square root of both sides to get the time. So this 2 pi r is really the time in my clock, if I'm an observer here, and then I'm here. So my clock advances by 2 pi r. The coordinate t advances by 2 pi, but that's just a coordinate. Who cares about the coordinates, right? So let me emphasize that point. So this interval of time, t is the difference is t equal to 2 pi. This is the coordinate t. But the difference of time by the observer at rho equal to 0 is 2 pi times r. Because the observer at rho equals 0, the proper time, ds square, is equal to r square times dt square. Right? So times for the observer are rescaled by r compared to coordinates t. Yes? Ah, you're right. Great point. You're right. The time to come back and forth, indeed, as you are pointing out, that would be the full period. Yeah. Good point. Yeah. This time to come back and forth would be just half of the period, which is what I drew here. Great point. Yeah. So to see the full thing, I would need to come back. You're right. So this is pi. Thank you. Pi. And this is pi r. And there is an extra factor of r. And here it's pi r. So it's 2 pi r divided by 2. It's half the period. Good point. Yeah. I throw, it comes back, and then it goes back, right? The full period is 2 pi. In time, in coordinate, 2 pi r in proper time. Okay. So what would be, so suppose this was, so the lectures could have started by saying, this is the definition of an ice cylinder. It has this variable rho, it has this metric, it has these growing factors here, and these growing factors make this a confining box. It becomes harder and harder and harder to go to large rho because of these confining factors. And therefore, you throw things and they come back. What would be the advantage of this picture? Is that it makes that clear. It makes it clear it's a box. You throw geodesics and you would see right away that they come and they come back. What's the disadvantage? You don't see the huge amount of symmetry that this object has. All this symmetry that all points are the same, that all observers experience the same thing and so on, it's much harder to see. It's obscured in these coordinates. And it's manifest when I tell you it's just an hyperboloid that's invariant under boosts. Right? In the same way that if I gave you the coordinates for a sphere in some crazy coordinates, for example, like stereographic, the center and the infinity look more important than the rest. And you don't see right away that they are all the same. But it has advantages, of course, as well. Namely, you can draw it more easily and so on. So let's study a little bit. So these geodesics I'm not going to erase, but I want to spend some time repeating what we just did. So, but in these new coordinates. Now, you see that there are two ways of getting geodesics. One way is we solve the geodesics. It's done already. You already solved. There's nothing more to solve. You just solved all geodesics already, right? So if you want now the geodesics in the other coordinates, just change coordinates. You know the map. So just take this and translate to what it means in terms of rho, t, and theta, right? And you get a complicated equation just from solving the change of coordinates. Right? So that's one way of solving. Yes? What was what, sorry? Rho is the radius. Rho is this radial coordinate. Being rho equals 0 is being here at the center. Notice that rho equals 0 means that these variables are in a circle of radius r. That's exactly the red trajectory here. This red trajectory is being at rho equals 0. Just rotating here. So this red trajectory would be the center of ADS. but with quotation marks, because the yellow one is also the center of ADS. It is just, they are related by a boost. Everyone is in the center of ADS. The red one likes to draw this diagram, thinking I'm the center of ADS and the yellow is moving. The yellow would draw the same diagram with the red one moving, right? But so everyone is in the center. Very good. So, right. So for example, one possibility that we see right away is that the red line, this one here is a geodesic, and this geodesic is what? It's just put rho equals 0 and change time. By the way, let me make one important comment. That I'm using time here, t, and here I'm using t. This is what's called the ADS global time. That's a coordinate of space-time, t. It labels points in this space-time. That t is a parameter along a geodesic that tells me where I am on the geodesic. They're not the same thing. I know this can be confusing. What can I do? Probably there is a solution, but I don't know. Okay. Is it clear? So t there was the proper time, right? And t there is a coordinate. That's why, I just erased, but here there was a cosine of t over r. And there's only cosine of t. Here, the time, this was by definition the proper time. And so it was 2 pi r. And so here we already got the correct physical result, 2 pi r. There, the periodicity is 2 pi, because it's a coordinate. But that's all compatible, because that you need to multiply by r to go from that t to this t. And so everything is consistent. The global time is the y-axis. Yeah, like I drew here. Yeah, this is the global time. Right? So this tells me the coordinates that I use here. Who measures which clock measures this time? No one. Right? It's a bit because of this factor of r squared in front. No, not true. No one. It's different from, say, Schwarzschild, for example. You are used, Schwarzschild, say t is a coordinate, and it's the time measured by someone at infinity. Here, no. Here, t is a coordinate, and no one measures t. Okay. But t times r is the guy in the center that measures. Okay? So no one measures t, but it's a very nice coordinate that is period 2 pi. So things come back in 2 pi in t. That means that an observer at the center, things come back in 2 pi r. Is it clear? Or pi r, because it's half period. Okay. No, great question. So the question was, what if the observer is at another radius? Being at another radius is not a geodesic. So let me draw that. So you see, this is a geodesic. Something like this that oscillates is also a geodesic. This is not a geodesic. You see, like we said, this is a box. So if you throw something, it comes back. So you cannot just be floating here. To be floating there, you need some jetpacks, right? You need some jet to be floating, otherwise you fall. Right? So now, you could ask, how much time does it pass for that observer that's floating between this point A and this point B? Okay, you would compute. You would find what's the coordinate time TA, what's the coordinate time TB, and what's the physical interval for the guy at the yellow line. what would it be? So if this is the coordinate time TA, this is the coordinate time TB, if I am an observer here, what is the difference of time in the clock of this observer? So what do you need to know? You need to know if this is rho equals 0, what do you want? You want to know what is this rho star? It's at some location rho star. Then you just plug, so what's the answer? What's the time? How much time passes? Plus. So what are you going to do there? You are going to plug the new row. Say it's a new row that's constant. So what happens when you plug that row there? So what changes from here to here? What variable changes? Only global time. The other variables don't change. So when you integrate, you just change global time. But what does it mean integrate? There's no global time, right? So that integration is trivial. So what's the time for this observer here? By the way, this observer, like I said, she needs to have some jets, right? That are so that she's not falling towards the middle. So what time does she observe between this point and this point if this is TA and this is TB? So R cosh of rho star times TB minus TA. Do you agree? If rho star is 0, it's R times delta T, like we said before. But otherwise, if you are at a different R, it's a bigger time. Right? So that's the time. Yes? Because it's a box. And we saw that geodesics, this yellow geodesic does that. Space increases and comes back. So things fall towards the center. You see, this yellow geodesic, if I translate it here, it does exactly what this yellow one does. But we could also ask, how do I see that this is a confining potential from this picture here? So let's do that now. So why do things fall? We know they fall because we solved it geometrically, and we know that it's a box as a proper box. This stuff is very important, what we are doing now. So I hope, so do ask if you have questions. By this factor? You see, because the relevant, what we are going to do is that along this line, this segment here, we want this proper time. But in this time, all that matters is that factor, R square cosh square of rho times dt square. This is d tau square, where tau is the proper time. As we evolve up, phi doesn't change, the angles don't change, the radius doesn't change, nothing changes, only time changes, so only this part is relevant. And now we take the square root, we take the minus sign, and we integrate this. But the integral, like we said, is trivial because nothing depends on time. This row is fixed, this row star, and therefore we get this. Thank you. All good? Okay, so how would we study this box? How much time do I have? Do I have time? 10 minutes, okay. Yes. Okay. So let's study geodesics in ADS-3. ADS-3 is perfect because it's really a cylinder. It's really exactly that picture that we drew there. So let's write the Lagrangian. The Lagrangian is 1/2 of the integral, and then I just put Gij, I just write the metric, but now the metric is there. So the metric is just minus cos square of rho times t dot square plus rho dot square plus sinh square of rho times some angle, I called it theta there, theta dot square. So this is the Lagrangian. And from this Lagrangian, I could write down the equations of motion, right? Yes? Good, great point. What is this dot? Is with respect to proper time. Now it's better not to put t here, right? Because t there is a coordinate. So let's use s here. S is the proper time. Good. Now, here it is. Now we could write the equations of motion. Let me write one equation of motion. The t equation of motion. It says that d dt or d ds of the derivative of the action, which is minus cos square of rho times t dot square, is equal to 0. Do you agree? It's just derivative with respect to t dot gives this without square. Sorry. Right? And derivative with respect to t, there's no t explicitly, only t dot, so it's just this. So this is the equation of motion. If I compute the derivative of this, and bring it to the usual geodesic form, I could, but I'm not going to do this. It's silly. If this is 0, it's much better to use the fact that this is a constant. And then you already have a first order differential equation. What is this constant? It's in fact another charge that you would get if you look here and see, oh, but this Lagrangian doesn't depend on time. This space-time, it's invariant under changing time. Nothing changes in this cylinder. And therefore, energy should be conserved. So this is nothing but energy conservation. So we can write energy is equal to cos square of rho times t dot. More precisely, I forgot here an r square from the metric, so there will be some r square here. That's just an overall r square, doesn't change the equation of motion. And so this is a conserved charge. So this is a definition of what we call energy. It's charge associated to translation in time, the fact that nothing depends on time, something should be conserved, and it's this. Similarly, theta is this angle, and things are rotation invariant. So the angular momentum should be conserved, and that would be r square sinh square of rho times phi dot. And finally, the velocity should be well normalized. So this square should be equal to -1. This velocity should be well normalized. And therefore, we would get that -1 is equal to whatever is here, to all this thing, to r square times minus cos square of rho t dot square plus rho dot square plus sinh square of rho theta dot square. That was the condition that the velocity was well normalized, and I picked the -1 here because I want to study time-like geodesics. And so you see that we basically solve this problem in a simple way, because using this equation, we can eliminate t dot. Using this, we eliminate phi dot. We plug them here, and I get from these equations, I get a simple equation of the form rho dot is equal to some function of rho and of these two conserved charges. right? And therefore, I'm done. So that means, right, d rho divided by this is equal to ds, and I'm done. Yes? J is angular momentum. Sorry, here it's theta. And here it's, yeah. So this would be energy, this would be angular momentum. That they are conserved would follow immediately from the another charge associated to rotations in theta, translations in theta, and translations in t. Or, if you forgot about it, once you would be deriving the equations of motion, you would immediately find dd something equal to 0, and you would immediately say this is a constant. But if you open up the parens and take derivatives, you would suffer. Yeah. Don't do it. Okay. I suspect I forgot this R square in the notes. But did I forget R square? No, I did not. Okay, I'm smart. Good. Okay. So you see that you would get an equation of the form rho dot square plus some function of rho E and J equal to 0, or maybe minus. I use here a notation, okay. And now you would analyze this function here, depending on the values of E and J. And what you will find if you plot this function is that this function, as function of rho, looks something like this, which means there are two values here and here where this function vanishes. You could set it to 1. Then lengths would be dimensionless, but you have in your mind to keep in mind that everything is measured in units of ADS radius. That's fine. Okay, in a way, we are already setting c to 1, the speed of light, right? There's no speed of light anywhere. So when we say time is 2 pi r, of course, it's 2 pi r light rays, right? I mean, yeah. Okay, so there are two values where rho dot equal to 0. And that is easy. That is just a statement that seen from the above, we have global ADS, and we are saying that there is two values of rho where rho prime is 0, and that's because rho is doing this. That is just. So this is what you see from the top. So the yellow one could draw some surfaces that would interpolate between this. That's what you would get if you would integrate this equation. And this is time here coming out of the plane. You are in the middle of ADS, and you see this friendly observer rotating like this. And now you could ask, how long does it take for me from this point to this point? How long does it take to do one full rotation? And you could compute. You would do the computation, which would be just that this integral here from the point from, let's compute from the minimum from this point to this point. Let's compute this interval here. Let me call this delta t. This delta t, which is the proper time, is what? It's the integral from what point to what point? From the two zeros there. From rho minimum to rho max. Very easy, right? Just compute the zeros of that function. Integrate this, rho divided by square root of that function, right? That function is clear how to get, right? Just plug this here. Then you integrate from minimum to maximum, you get a number. And that number is how much time passed for you. Now, if you do this computation, what will you find? We know the answer already. What's the period for you? 2 pi r. So what should you get here? What fraction of the full period from here to here? 1/4, right? So instead of 2 pi r, the answer of that computation, if you did no mistake, must be pi r over 2. It's still a nice exercise to check there was no mistake, right? Plug E and J, compute the turning points, integrate from turning points, do this integral carefully or numerically and so on, and check that it is pi r over 2 and that you get pi r over 2. But you will get pi r over 2. It's going to work. Right? The last thing we could do, so this was for a rotating geodesic. An extremum case of this rotating geodesic, so there are two extremum cases. One is when it rotates in a circle, and the other is when it draws a very thin ellipse, in other words, when it just comes back and forth passing by the origin. Right? The two extreme cases of this is circle and just rotating back and forth. Right? So this one is very easy to solve, because what is the angular momentum in that case? What is theta dot? If I'm just always in the same plane, going back and forth, theta dot is 0. The angle is not changing. So you can immediately drop theta dot, drop here and here. T dot depends on the energy. But now you would write an equation. There would be just a maximum that it would go, and then it would come back. Now, if you integrate in that case, you would just find that the particle goes like this. In the case when you solve those equations with j equals 0, just evolving this. Right? And again, if you were to compute the time from here to here for the observer in the middle, it would be always 2 pi r. If you ask how much time is the proper time, it's also 2 pi r, and so on. Provided you do it carefully between the correct points. And this is worked out carefully in the notes. So that answers your question, who asked why does it fall towards the box and not outside? We saw it already before geometrically. Here is the geodesic, going far away, coming back to the center, going far away, coming back to the center, going far away, coming back to the center. And now we see it again. We have the rho dot that has a maximum and a minimum, and it goes back and then forward and then back and then forward. And so it doesn't look only like a box, it's a box. Okay? Okay, very good. So we managed to catch up. I think today I did more than I thought I was going to do, so I'm happy. Very good, thank you.
Yeah, a question. What happens if we go outside the range of the box? There's another maximum somewhere over there, or we'll always be in a box?
No, that's not accessible, because this function that I'm plotting here is this f. And this f, actually what I'm plotting is minus f. So that minus f needs to be positive. Otherwise you cannot have rho dot. So you should think that when the particle gets here, rho dot is 0. It has 0 kinetic energy. Then it goes back. So classically, the particle can only live here.
Right, yeah.
Here, the particle would have imaginary energy.
Because it has
so
to
quantum
be
mechanically, for example, there will be a wave function here, and then it will decay exponentially outside. But classically, that's the only allowed region. It's where the particle can move there. So it needs to have enough angular momentum to have a place to rotate and so on.
A more conceptual question. If being on a timeline geodesic is just to remain in space and let time go, be in a space like geodesic will be like moving in time, nor moving in space without moving in time?
Yes.
And what will be a null geodesic?
That's not a physical observer. That's why I said persons, people go a long time like geodesics. Let's remember in flat space. If I am in flat space, what's an example of a time-like geodesic? Just this bit. This is time-like. Another time-like geodesic, some spaceship that moves like this. An old geodesic, something like this. So this one is null. And a space-like geodesic, something like this or something like this. These ones represent lengths at fixed time, but there's no observer that goes there, right, in flat space. This is a space-like geodesic, time-like geodesic, null geodesic. Okay. Photons go at null geodesics, people go at time-like geodesics, and rulers measure space-like geodesics, but they are not observers. Well, let me make a related comment. How do we measure a distance in flat space? What's a useful way of measuring a distance in flat space? Rulers? Photon, yeah, very good. Line. So you send a photon, and it comes back, and you measure the length. Right, you measure this time, and the time that the photon comes back and forth, you divide by 2 because it's going and coming back, and that gives you the length of this segment. Now, suppose I try to use this here. So I throw something, and it comes back. In the extreme case of sending a light ray, it's the case that goes exactly to the boundary and comes back. So you see that the light ray goes all the way to the boundary and comes back. How much time does it take? 2 pi r. But what was the length? Infinity. So it's a bit, you cannot measure distances in a curved space-time by sending light ray and coming back, because distances and times are deformed along the way. Here, no matter what you throw, it comes back in the same time. You throw it stronger, it comes back in the same time. So, right? So you throw something with not too much strength, it hits someone nearby and comes back. You throw it much stronger, it goes much further away and comes back at the same time. But it hits different people at different lengths.
But how do you measure?
It depends. A way of defining a proper length here, for example, if I want the length from here to here, right, I would say that in this length, what is changing in the metric? Time is not moving, the angle is not moving, so only rho is moving. So what would be the distance here? If this is rho equals 0 and if this is rho equal rho star? This distance L? You didn't forget. I thought you would forget the R. Yes, R times rho star, because there is 1 over R squared here. So you need to multiply. Right? So the proper length of this segment would be R times the rho star. Right? So that's this length. How long does it take for a particle to go here and come back? 2 pi R.
But
No, this is at finite rho star. So this.
I know. I mean the other.
The other length.
A consequence of the way we are.
No, it's really infinite. It's really infinite in the sense that if you are here, you could put a small ruler, and then you go to the end of the ruler and you put another ruler, and then you go to the end of the ruler and you put another ruler, and you keep doing it, and it never ends. You would just say, after 1 million rulers that I go close to each one and I see 1 meter, I'm still going, and it doesn't end. It is just that as I'm moving further and further and further and further, time is becoming more and more dilated in these rulers, so that when the photon goes back and forth, it comes back in a finite amount of time, even though it went through an infinite amount of rulers.
Thank you.
So my question was sort of like about what you said. When you talked about null geodesics in ADS2, I thought that because they are just geodesics in the embedding space, that if you threw a light, ever come back. But it seems not the case, right?
Whether it comes back or not depends on what boundary conditions you put. Because if you throw a light ray, it barely manages to touch the boundary at infinity. Now there, you have the freedom to say, there's someone there that catches the photon and keeps the photon. Or it reflects. So you need to specify the boundary conditions at infinity. Assuming it's a wall that things bounce, then it comes back. But you need to, because it reaches the boundary, you should tell me what should I do if a photon comes to the boundary. Is there a detector and it stays there and just makes a noise? Or is it a mirror and it comes back? Null geodesics is something I didn't have time, actually, I realized. That's the very last part of the note, 3.3 of this lecture 3. So next time, I will discuss a little bit about this null geodesics in more detail. But I will not come back, I think, to time-like geodesics, which are very important. And I hope this lecture was clear. But everything is in the notes as well. So do try to study it again if something was not clear. Yes? You can, yeah, it's going to be faster than me.
Sorry. Can I understand that F function as a effective potential?
Yes.
So I
Yes.
can study the stability of the geodesics by that graph.
Yes, you can. Yes. It is an effective potential, right? It's this equation. If I were to write, if I don't like this equation and I want a standard equation, rho dot dot equals something, that's fine. I just take the derivative and I get rho dot dot equal to some function. And then that function is like a Schrodinger equation and it will, but yeah, that's what I explained here, right? There are 2 points of equilibrium and,
Okay.
But it's stable in this case, in the sense that if you have this particle, it goes back and forth in a box.
Mm-hmm.
What would happen if you kick it a little bit? It would go in an ellipse. It would open up a little bit, slightly. But it's a box. It's really, imagine you have a box that's confining and something is oscillating. What happens if you go there and kick it a little bit? It wobbles a little bit, but it will keep oscillating, right? And you hit it a little bit, and it goes to a slightly different ellipse, but it keeps oscillating. It's confining, so it's very stable.
So every geodesic in this case time-like is...
All time-like geodesics are periodic. They all have proper time 2 pi r, and they are all the same because they can all be related by symmetry. However, when I have more than one geodesic, there are interesting questions about the relative separation and the relative behavior of the 2 geodesics, right? So any time-like geodesic, the experience of that observer is the same. For that person, he or she is in the middle of ADS, quiet, doing nothing. And then they can see something coming back and forth or something orbiting around, and those look different, of course, right? If something comes back and passes by you, it's different from something rotating.
Okay. Thank you.
So it's a box. All geodesics are the same. Everyone is the same period. So it's very, 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 very symmetrical box, right? So it's a box where everyone is at the center of the box and everyone experiences the same thing. Yeah. Oh, you have it already, right?
Okay, so let's thank Pedro again. So we have a 15-minute break, and then I think we